Okay, so I've been playing around with prime numbers like a lot of people have, and I just want to say at the beginning of this video that I'm very much a novice, and I fully realize that what I came up with here may be something that mathematicians discovered 500 years ago, or maybe it's not a pattern at all. Maybe it's not predictive of future events. In fact, I'd be willing to bet that all those things are the case. But I I I read a lot about prime numbers, and I got sick of reading what other people had discovered, largely because a lot of it was beyond my scope. So I just started playing around with the numbers on my own, and here's what I did. I put together these prime number distribution clusters in 10-digit clusters. So the first one being 1 through 10. So in that cluster, then the digits 2, 3, 5, and 7 are prime. So this number over here in column K represents the fact that there's 4 prime numbers in that cluster. And each subsequent cluster, same thing. So second cluster of 10 digits, we have 11, 13, 17, and 19 are prime. Also, all 4 digits, all of the 4 potentially prime digits. Whereas up here, I guess in that first cluster, there could have been a 5th prime number, but 9 is not prime. So the two clusters that I was most interested in are 4-digit, are 4 prime number density clusters and 3. So the places in the number line where there's higher density prime numbers. And I wanted to look at the distance between those clusters, as you can see over here in this little table I put together. So for 4 prime density clusters, the first time we see it is in row 1, the second time is in row 2, difference being 1, and then each subsequent 4 prime cluster, I have the rows here and the distance between them here. And one thing that all of these numbers highlighted have in common is that 3 goes into them evenly. We have one anomaly up here. 3 doesn't go into 1. It can't go into 1 because it's bigger. And maybe that has to do with the fact that number 2 has been granted the distinction of being a prime number, which I guess is the kind of a contentious subject among mathematicians. So that's the 4 prime density clusters, and here's 3 prime density. First occurrence is in row 5. This is not accurate. The first occurrence in row 5, second in row 8. So the distance between those is 3, 6, 9, 9, 12, 18, 27, and so on. And obviously this table can get extended into perpetuity, which again, I'll leave it for somebody more techy and knowledgeable than me to figure out if this is an ongoing trend. And again, it might not be a pattern, it might not be predictive of future prime numbers. It could be that this density of prime numbers balances itself out because the three prime clusters are not in a pattern with the 4 prime clusters, and maybe that's just it is randomized somehow. I don't know. Again, this is questions I'm not capable of answering, but I found it interesting, and just as I'm saying this, I'm thinking, maybe the 2 prime clusters have some sort of pattern as well. So first one is in row 3, next one in row 4, the difference being 1. Then here we go down to row 6, difference is 2, difference is 1, difference is 2. Then we have to go all the way from row 9 to row 16, the difference being 7, and then 1 and 1, and then we go from row 18 to row 24, difference of 6. So I'm not sure if there's anything going on there. I just was focusing on the 4 prime clusters and 3 prime clusters.